So thanks everybody. Just would like to add to this, Marco. This will be the first tectonic special issue dedicated to someone. So we're very glad to, and we invite all of you to submit a good and regional contribution. There will be a good occasion to start for tectonics, and also the good thing is that we don't have to wait that the whole volume is completed, because tectonic go online. So once you have your paper, gonna be ready and gonna be reviewer can be appear online. So it should be a quick and fast procedure. So thanks Gerardo and Rodolfo for the initiative. So I'm here just a few minutes because we are already far out of time to introduce Wiki Royden. It's a big pleasure for me. Well, Wiki, she's a professor at MIT from faculty from like 88 or something like that. We don't want to remember that. 84. She has a list of awards that the last one was in Vienna AGU. She received the Stefan Müller Medal, a very prestigious medal. She has a GSA meeting fellowship. She was a fellow of AGU and the Academy of Science, etc., etc. So I don't want to say. But for many of us, Wiki is already a well-known scientist because of her fundamental contribution with Paolo that we remember today and Etta on the origin of the Ferriday Basin and on the Apennine. So with this contribution, we can clearly illuminate the way the Mediterranean subduction system work and introduce concepts that are now for us all established on the slab pool and the significance of that. And so basically what Wiki have done during his career is using sedimentary record and sedimentary basins since the early 80s to understand, for example, the rheology of the lithosphere, how it works, and process like the dynamic of subduction. And for the mountain building, for example, the way the mountain building, the form, she gave a fundamental contribution on the problem of the viscous weak flow on the lower crust. So applied to the basin range, for example, or it applied to the Tibet, giving a seminal importance. So now, in more recent time, Wiki really dedicated her attention on subduction process, and she make a lot of progress on understanding how subduction work, and I think the today talk of Wiki will be dedicated to that, on her recent progress on that. Mostly what I think it's the last message I would like to give before giving the floor to Wiki is that she is an example how really geological constraint, geophysical modeling, and geophysical constraint will emerge together to illuminate the way large-scale continental deformation. So thank you, Wiki, to be here. I'm very glad, and the floor is yours.
How do I advance? How does I advance the slide? Oh, and I can go backwards also? Okay.
And then the pointer is the red light.
This
Yeah.
one? No, this one.
Yeah.
Oh, okay. Right. Well, it's a great pleasure to be back in Italy, whereas Claudio said I did some of my very first work, which helped form my thinking about my career with Paolo Scandone and Etta Patacca, and also a sadness to be here without Paolo. So today I'm going to talk about, if I have time because we're starting late, but I'm going to begin talking about subduction and some theoretical things that come from modeling, and then try to give you one practical example which relates the modeling to the geology in looking at subduction. So looking at this map of the world, the point I'd like to make is that one of the I think most important things in tectonics that we do not understand are the organizing principles for plate tectonics. We know what drives the plates, which is mainly subduction, and I think actually entirely subduction with some small contribution of plumes, but we don't know what organizes the plate system into approximately 10 major plates and approximately the same number of continents. And if we're going to understand that, we really need to understand the subduction process better and how subduction systems talk to each other, both by through mantle circulation and through stresses transmitted through the lithosphere. And this is especially true if we're ever going to be able to understand early Earth history, how tectonic systems worked, or whether tectonic systems worked in the early days of plate tectonics. So what I'm going to start with is some modeling results which are based partly on numerical models and partly on purely analytical models. So those of you who know me know that I don't really do these large numerical models, and all of the models that I'm going to show you were done by a graduate student, Adam Holt at USC, working with Thorsten Becker, and all the more analytical work was done by me in a collaboration. So basically, this is not what I meant to do here. Can we go backwards? Is it going backwards? All right, this is a little confusing. Okay, so basically what we're doing is looking at subduction in 3 dimensions. And as I'm going to show you, subduction, especially when you look at more than one plate, is fundamentally 3-dimensional. And so we're going to start with a variety of numerical models that basically consist of 1 or 2 plate systems with a subduction zone. Here you see in profile. And here looking at the top surface with trench lengths that are 2,000 kilometers long. Now, of course, the buoyancy of the slab, or negative buoyancy of the slab, is the main driver for subduction. The forces that are generated, the negative slab buoyancy is immense, about a factor of 10 or more larger than the stresses generated by ridge push. But most of that is counterbalanced by what's happening with the viscous resistance down here within the mantle. But remember that there's an enormous reservoir of potential energy there to drive subduction and convergence. So in this talk, basically, we're going to be looking entirely at things that have a fixed trench length here of 2,000 kilometers, although the geometry and the spacing between the slabs will change, and also a fixed slab buoyancy, which you can see down here is something that corresponds roughly to old oceanic crust. And this is right, and the second thing that we're going to do is look at the same situations analytically, where basically, analytically, if we start with a situation like this, we can divide the flow into 2 components. A regional component, which basically can be calculated simply by treating the slabs as vertical boundaries, which move through the asthenosphere, and also by looking at the motions of the surface plates. And there's an approximation called Healy-Shaw flow, which works quite well for this, as I'm going to show you. So we have this regional scale flow, and then and this works everywhere except locally near the slab, where we have to worry about a wedge flow, which is especially important in the narrow ends of these wedges above and below the slab. So, of course, in numerical modeling, there is no difference between regional and local flow. It's all calculated simultaneously. In the analytical models, we can distinguish between or separate out these 2 mechanisms. So first, let's look at some numerical results just for reference of a single slab. So here we start with a slab dipping at 70 degrees, allow that to go forward through time. And I should say it's important to know that all of these models are fully dynamically consistent. So we don't drive any plate motions artificially. Everything happens just as driven by the weight of the slab sinking through the asthenosphere. So in this particular case, this slab reaches a steady state of about 70 millimeters per year, something similar to old oceanic lithosphere. And the dip starts out somewhere around 75 degrees and gradually decreases through time. So when we look at this, then we can also make some pictures of what's happening here. So here we see this slab at fairly early times, and the colors represent the pressure, the dynamic pressure, or the viscous pressure within the asthenosphere. So the blue, it would be negative pressures, and the red would be positive pressures here. And ignore the colors within the slab. They're mainly reflecting, they essentially are saturating the color scheme and are not especially meaningful, as well as the colors just at the very top of the model. So here you can see this slab, which starts out here with time, and then the subducted portion gets longer as the surface portion gets shorter. And you can see again the same kind of pressure distribution, high pressures beneath the slab and negative pressures above the slab. All right, so now what I'd like to do is show you, so that's a numerical result, and by the way, the arrows are the velocities of these slabs here in some absolute reference frame. Now what I'd like to show you is what we can do analytically and what the understanding is that comes out of that, which is maybe not obvious from the numerical models. So for this analytical approach, even though I only show you a cross-section, this is also a 3D with a trench 2,000 kilometers long in this direction. There are a few differences in setup between this and the numerical models, but for all intents and purposes, they're virtually identical. And I should also have mentioned there's a stress-free boundary here at the base of the upper mantle, and we don't allow the slab to go through, at least not in this particular set of models. So for the analytical models that I'm going to show you, all we need to know for this are 4 points. The endpoints of the slab at the surface, the endpoint of the subducted slab at depth, and the position of the slab at mid-mantle depth. We don't need to know the location of the trench, okay? So we're only knowing these 4 points. And what we do then to calculate this regional flow is we just have a stationary slab. Well, we can compute it relative to the trench. So relative to the trench, this slab is stationary. This one is moving in at the subduction velocity. And then the slab along the base of the mantle is moving out at the subduction velocity. And of course, this won't take care of the pressures in the wedge up here and down here. But for right now, let's not worry about those. We're just going to compute the pressure everywhere else within the mantle. So this is all we know are those dots, and we connect them up with the black lines. So using only this, here now we're computing the pressure in the asthenosphere. So this is the dynamic pressure. It's the pressure that is driven by and also drives some motion within the slab. So you can't say the slab drives the asthenosphere or the other way around. It's a consistent dynamic system. And so basically one of these lines, I guess the lighter green one, is the analytical model, which runs in like 1/10 of a second or less on my laptop. And the green is the numerical solution, which takes several days on the supercomputer to run. And we're looking at a solution basically right along this cross-section for this first time period here. And you can see that basically the analytical solution, which is this very, very simple mathematical solution, and the fully numerical solution are nearly identical. And here's the location of the slab. So you can see the high pressures generated here under the slab, the negative pressures here over the slab, and this is at mid-mantle depth through here. And notice that there's a pressure difference. This is important across the slab, and in this case, it's 18 MPa. So remember the number 18 for just a moment. And now we come to a later time period, this one here, where we have subducted more of the slab. And you can see, again, comparing the numerical and the analytical model, you can see not identical results, but very, very close. And again, here's the position of the slab here. And in this case, the pressure difference is larger. It's 25 MPa, although the signal, the shape of the signal is really quite similar. So can we understand why this system wants to evolve a negative pressure on the top of the slab and a positive pressure on the bottom, and what this actually does in terms of setting the dip of the slab? So let's start by thinking about everything relative to the trench. So these velocity arrows here are not relative to the trench, so ignore those for the moment. Let's just consider everything relative to the trench. So the subducting slab moves in like this, hits the trench, and then here on the bottom of the mantle, the subducting slab moves away from the trench. Okay, so if we think about this just as a 2D problem for a moment, if I take a cross-section, say through here, as this slab moves out, it has to bring material with it through shear stresses. It's dragging material out away from the trench along with the slab. So that means that material, we have to have essentially zero net flux through here, which means that material has to move in this region in order to balance the outflow of material down here. This can't be driven by plate motions relative to the trench because this plate is not moving. So this has to be driven by a pressure gradient. And we can see the same thing for the upper plate. This plate is moving in, it's bringing material with it, so there has to be an outflow of material here, and this also has to be driven by a pressure gradient. So material always flows from a region of higher pressure to a region of lower pressure. And so in this case, for material to flow in, it has to be going from higher pressure here to lower pressure here. For material to flow out down here, it has to be going from higher pressure here to lower pressure out here. And because we're at near zero pressure on the ends of the box here, we have to have a decreasing pressure, becoming more negative as we move in, and then here the pressure has to be more positive as we move in. So basically, this pressure difference, positive on the bottom and negative on the top, is a result of counterflow, which is basically counterbalancing this outflow of material. Of course, in 3D, some material comes out the sides as well, but the general result is still the same. All right, so now that we understand why this kind of geometry gives us a positive pressure down here and a negative pressure here, can we say more about this? Can we understand something about the slab geometry in very simple ways rather than just, looking at a very complex numerical model and seeing the results? And I'm going to show you that we can do that by using some analytical methods. So in this case, the slab is more or less straight or planar as it comes down through here. Not completely, it's got some flexure, but let's just for the moment imagine that it's mostly planar through here. Now this is a negatively buoyant heavy object, and so there's a gravitational force or buoyancy force on it that acts straight down. We can break that force up into a component, so here's the straight downward force, into a component that acts along the slab here, and in a component that acts normal to the slab. This slab is not very curved. It means that we can't use flexural stresses to support any of the load. So the component that goes along the slab can be supported by stresses going up and down the slab, but the component of this buoyancy force that's orthogonal or normal to the slab really has to be supported by viscous pressure acting on the slab. There's no other force to support it. So let's follow along with this idea and see where this leads us. Okay, so here is a plot of pressure difference across the slab. So here's no pressure difference. And then this, as we move down here, it means more negative pressure above the slab and more positive pressure below the slab. Now, if buoyancy forces normal to the slab were exactly supported by the pressure difference, we would expect to be right on this line right here. So here's dip across the bottom going from 40 degrees to 120. So the flatter the slab is, the more pressure difference you need to hold it up. If it's a vertical slab, you essentially don't need any pressure difference to hold it up. All the stresses can be transmitted straight up the slab. So that's why here at 90 degrees we have zero pressure difference. So these solid points here are the result of a number of different single subduction runs once it's reached a steady state or quasi-steady state. And you can see the trend is right along this line with an offset of about 5 degrees. And we're not quite sure whether the 5 degrees is a flexural component or whether it's actually something to do with a numerical solution that we're still sort of fiddling with this. And even before this reaches a quasi-steady state in these points here, you can see that there's still this general trend where the pressure difference across the slab and the dip of the slab are very strongly correlated. So if we know one, we more or less know the other one. Okay, so now what we're going to do is go to the analytical models and see what else we can say. Actually, let me just back up for a second. So here, if we look at this, something like this, the faster this subducts, the higher pressure is going to be generated because that pressure is being generated by the moving slab. A faster slab, these are Newtonian models, will generate a higher pressure. So let's suppose now for the analytical model that we don't really know anything. We don't know how fast the slab is subducting. We don't know the angle of subduction, but we know the geometry of the plates. Then I can calculate, here's subduction velocity. I can calculate as a function of subduction velocity going from 0 to some 120 millimeters per year, I can calculate the average dip of the slab. So here, if I'm vertical at 90 degrees, I don't need any pressure to support the slab. I need to be pulling up on the slab towards the surface, but I don't need anything to support it in this sense. And so now as the dip of the slab shallows, I need more pressure on the base to support it. The reason this curve turns over here is that these wedge stresses that we're ignoring become important when the slab gets flat. So if I just looked at the regional pressure, it would keep going up like this. Okay, so basically what I can see now is that the dip of the slab can be supported by the pressure difference across the slab anywhere along this line. So my slab conditions have to lie somewhere here. So how does the slab know where on that line it wants to be? And of course, the answer is that supporting the slab normal stresses here is not the only important thing. We also need to balance all the horizontal and vertical forces on the slab. And this is actually harder, much harder than just balancing the dip of the slab. So we need to consider the shear stresses acting on the slab. And there are also shear stresses and some normal stresses that occur right here at the contact zone. And so in order to compare our analytical modeling to the sitcom models, we had to do exactly what they did here at the trench, which is just put some viscous, very weak, gooey cross down in here to lubricate the system. So it's not something you would normally maybe want to apply to the real Earth model, but since we want to understand our analytical models and our numerical models, we have to make them look similar. Okay, so this line that you see here, this lighter blue line, is basically the relationship that we get between subduction velocity, again, and average slab dip. But in this case, we're not looking at the angle of the slab. We're balancing, or we're not computing the slab normal support. We're balancing the vertical and horizontal forces acting on the slab. So in order for the vertical and horizontal forces to balance, the relationship between subduction velocity and slab dip has to fall somewhere on this line here. So then the result is one would predict that where these two lines cross is the place where we satisfy both the horizontal and vertical force balance on the entire system, and we have a slab dip which is supported by the pressure drop across the slab. And there, sort of anomalously close, that's the numerical solution right here. So here's the simple analytic solution that, again, I have a code on a laptop that runs in less than a second. And here is the result of the big numerical model giving us the slab dip and subduction rate right here. So often our results aren't quite this close together, but typically they're within about 5 degrees and 5 millimeters per year in velocity. Okay, so now let's look at something a little bit more interesting. That was basically important because we understand that there are certain rules now for understanding the behavior of these slabs. And I want to show you that the rules are basically the same when you look at more complex systems of subduction. So we're going to look at now the next simplest system that we can see, which is a system where we have two subduction zones and the slabs dip away from each other. They're identical slabs. The trench length here is the same. It's 2,000 kilometers. Everything is the same. And what we imagine is before, remember, we had high pressure built up underneath the slab and low pressure on top. Here we guess that the pressure is going to be a lot higher. Why? Well, because here the intermediate plate is being subducted, so the two slabs have to become closer together with time. As the slabs become closer together with time, this volume here has to decrease, which means material has to flow out, basically away out of this zone in the third dimension, so towards you and away from you into the screen. And so we expect this will generate higher pressure, and that the closer the slabs get together, the higher that pressure is going to be because it's harder to force that material out within a narrower and narrower zone. Okay, so here are, again, we're looking at a cross-section, but these are three-dimensional models. So here is this double out-dipping subduction system starting from an early time. You see the trenches converging here, and then finally, we can't do this analytically, we can't handle the case where the trenches disappear from the surface, but numerically you can get a solution that looks something like this. So if you look at the convergence rates now, this gray line here, and I'm sure you can't read this, but it's about 70 millimeters per year in steady state. This double subduction, each trench or each subduction system subducts at about 55 millimeters per year. So the rate's slowed by about 25% for each subduction system, but added together, you're about 50% faster than you were before. So this elevated pressure in here is basically slowing down the rate of subduction. Okay, so now let's look at the profiles of the pressure that's developed. So here are 3 different time periods in green, blue, and red that correspond to actually not quite these 3 stages, but basically a decreasing width between the the trenches. So in each case, the vertical boundary is the slab. And what you can see is, first of all, the analytical and the numerical models are very, very similar. So just by using this simple analytical technique where we treat the slabs as vertical boundaries and look at the geometry of the plates, we can basically reproduce this regional pressure field at upper mantle depth. And also, there's a scale over here, but basically here the pressures rise to 40 or more than 40 MPa. And remember the single slab model, we had 18 to 25. Here we have 20 to 40 MPa. So in these first cases here, basically these two slabs don't see each other very much. The pressure's not that much different than in the single slab case. But as they get closer and closer together, these pressures get extremely high. So this is interesting because it tells us about double slab subduction, but it's also interesting because it extends the range of parameters. It extends the pressure range over which we can examine subduction. So these blue dots here, so the black is the single subduction case. These blue dots that go from here to here are the pressure difference across the slab plotted against slab dip, the same as we saw before. Here's the relationship for supporting the slab entirely by the pressure difference across the slab. And again, you can see this trend is basically, we're almost completely parallel to this line. We don't quite understand what this small offset is. But basically, this shows that the pressure difference across the slab is closely correlated with the slab dip and largely supports the slab. Okay, so now let's do the same thing we did with the single slab case. This is completely analytical. We don't assume anything about plate velocities. We calculate them. So here, what we're looking at is subduction velocity versus slab dip again. At 90 degrees, just like before, we have a vertical slab. Doesn't need any support in the slab normal direction. And as the velocity of subduction increases, it can support a flatter and flatter slab, again, until we get into the very flat slab region. So for double subduction, one of the slabs, either of the slabs, should be happy being along this curve here. And then again, the question is, how does it choose a particular point? Well, again, we do a horizontal and vertical force balance. In this case, we have to do it also on the entire system. So this is a horizontal and vertical force balance on all three plates simultaneously. And we find basically an average slab dip versus subduction velocity for this force balance. Looks something like this. And then here is the numerical result, basically sitting right on top of this point. Again, correlations may be a little bit better than is realistic. So finally, let's go to now a case where both slabs are subducting in the same direction. Again, we expect high pressure here, maybe not so high as in this case, but higher than in the single slab case, because you see as this slab subducts here, the distance between the slabs is decreasing. So again, material has to get out by traveling in this third dimension. This slab basically is going to probably experience conditions pretty similar to this one or this one with a high pressure beneath. But notice this slab has a very different situation. The high pressure is developed on the top of the slab or on the overriding plate of the slab, not on the underneath part of the slab. So let's look at this now. Here are the numerical results, and you can see two things. The first one is this slab is pretty happy being right side up. But this slab doesn't want to stay in a right side up position. You can see it folding, and it looks like it's trying, well, it is becoming overturned. It looks like it's trying to become fully overturned. Now let's look at the convergence rates. So I hope you can see this on the lower part of the screen. But this gray line is, again, the single slab case for reference at 70 millimeters per year. This slab here, which I'll call the front slab, that's pretty happy. That's all, looks like it's in steady state. It's very slightly slower, but everything about this slab looks pretty similar. But then the rear slab, the one that's folding, it never reaches a steady state. It basically has this oscillatory behavior as it tries to turn over. The trench advance isn't regular. If we look at the pressure versus dip, we see this front slab, the one that has the high pressure underneath. It looks just like the other slabs we looked at. And again, the pressure difference across the slab and the dip of the slab are closely correlated. But now let's look at this rear slab, this one that's turning over. It has an irregular rate of trench advance. It's nowhere near to being in a steady state or quasi-steady state. Its pressure dip starts here, and it moves off this track and over here somewhere. And it basically, I think this is because it's folding, it's bending very sharply. There are a lot of flexural stresses within the slab, and so for this transient behavior where things are folding up and bending, this relationship doesn't really hold. Of course, that's only a transient behavior, and we can see that this slab looks like it's trying to become upside down. So what happens if we start it? This is a second set of runs down here. If we start this slab upside down instead of right side up, we watch that evolve through time to some time later here. It's very happy being upside down, and the high pressures within this interslab region are pushing this out to the left here and maintaining this in an overturned position. So basically the regional pressures that are generated by these slabs basically talking to each other can be understood as also changing the local geometry of the slab. So, and when we start this in the overturned position, we can see both the front slab, this one, which started right side up and stays right side up, and this one, rear slab, which starts upside down and stays upside down, are both very happy along a steady state that's about the same as the single slab reference case. And so in this case, basically, the slab's not quite on this line. It starts here. It's approaching closer to that line. It's also got some curvature. It doesn't have as well a defined dip as these slabs that are right side up, but it's basically falling fairly close to this line here. And then finally, and quickly, we come to this in-dipping slab case where in this case, the distance between the trenches is not changing, it's staying fixed, and so as subduction occurs, the trenches stay the same distance apart. And you can basically see here from this pressure plot, colored pressure representation, that there's very little pressure difference across the slabs. Pressures are small everywhere here. And because of this, this slab is very happy whether it starts right side up, it stays that way, or upside down, it stays that way too. So it doesn't really have a preferred orientation. And the convergence rate, interestingly, in the upside down position is close to the single slab. In the right side up position, it's quite a bit slower. And these, in both cases, these plot right on this theoretical curve between delta P across the slab and slab dip. Okay, so now what about ridge push? So when we talk about mechanisms that move the plates, we know subduction is really important. Ridge push is thought to be, depending on who you talk to, maybe 15% of what drives the plates. And ridge push basically is not a push; it's a pressure or buoyancy acting on the ends of the plates at the oceanic spreading zone and acting on the base of these plates as they thicken. But in modeling land, basically, where the plates don't thin towards the edge, they have an abrupt end, it's basically just a pressure applied to the plate end. And this is one of the advantages of doing analytical modeling, is you can take ridge push off and put it back on again, which you can't do in the numerical models because it's completely coupled in to the system. So if you imagine that we have this system and we push, let's say, harder on the ends of this or through ridge push, or we take away the push, what's going to happen? Well, it entirely depends on what happens at this boundary that couples the overriding plate to the downgoing plate. So if the forces are transmitted basically by shear stresses on the plate, then at this boundary we're adding an upward shear stress to the downgoing plate. This will slow subduction down. But in the other end member, suppose there's no shear stress here, and basically the additional compression is transmitted as a normal stress. This basically pushes the subducting plate down in that direction and will speed up the subduction. So actually how you do, what the result that you get depends strongly on what it is that you assume at that boundary for the way the plates are coupled. So for the numerical models that we're using, basically it turns out most of the coupling is through shear stress. So one of these plots, again, here is the support of the slab, normal by the slab normal component of pressure. And then we can look at vertical and horizontal force balance with and without ridge push. And you can see that this plot indicates there's something like only a 5 millimeter per year difference in rate and a 5 degree or so difference in dip when you add a ridge push into the system. So ridge push does a little bit, but it doesn't do very much. It's down in about the 5% range of being important in terms of changing the velocities. It changes the stresses, but not really changing the velocities. So now let's look at what happens when we have a different material that we put in here. So, you know, people talk about strong coupling and weak coupling at these subduction boundaries. And so for the numerical models, all you can really do is you can feed weaker viscous material or stronger viscous material into this zone through here. So that basically, and this is one of the limitations of the numerical models, this weak crustal material, it actually has the same density as the lithosphere, comes in, it gets pulled down the channel, and numerical models can't make subduction work unless they do this. It's one of the disadvantages of them. So anyway, we can change the viscosity of the stuff we feed into here. It was the same viscosity as the asthenosphere before and 500 times less than the plates. And we can make it 10 times weaker than that or 5 times stronger than that. So here's our original subduction rate. If we have a weaker material, subduction goes faster, almost a factor of 2, and then it sort of slows down through time. If we have stronger material, the subduction rate goes much slower than it did before. So let's see how we can do, and those were numerical results. Let's see what the analytical stuff tells us just by doing these very simple force balances. So here's the relationship between velocity from 0 to 150 MPa on the vertical axis and average slab dip on the horizontal axis. So here is the normal support of the slab. So we're just supporting slab dip with the slab normal pressure. Looks something like this. And then here's the line that represents vertical and horizontal force balance on the slab. Those two things cross right here. And there is the result from the numerical code. Basically, we're pretty close. Now let's look at the case where we have this very strong material in the crustal channel. This curve looks almost the same, and that's because the strength of the material between the two plates really doesn't affect the fact that if for a given plate geometry, change in pressure and the change in dip are basically the same. It does, however, greatly affect the vertical and horizontal force balance line, which is down here. And we look at the places where those intersect. The analytical model predicts that, and is the result of the numerical model. So if we summarize at least some of this material, asking whether these sort of simple analytical insights that we have are how well that we can reproduce the numerical models. And this means that then we can use the simple analytical insights to understand subduction. We can see the comparison here. The analytical is the dot, the numerical is the square. And here's the single subduction zone that we started with here. Here's this double out-dipping subduction system. Here's the single subduction system with a strong interface, and here's the single subduction system with the weak interface at early times, 4 million years, and at later times, at 12 million years. So we can actually see that the analytical model reproduces the numerical model in seeing how these rates evolve through time as we develop a longer piece of slab at the base of the upper mantle. Now, this is also, we've been only looking at things with a trench length of about 2,000 kilometers, or exactly 2,000 kilometers. And analytically, you can show that basically the subduction velocity for a double system is for a slab separation of 1,000 kilometers. If the trench length is very small, basically you just get twice the single slab rate here. As the trenches get longer for a fixed separation, the convergence rates and subduction rates get slower and slower. So when you have 3,000 kilometer long trenches that are only 1,000 kilometers apart, you're getting down to single slab subduction rates across the entire system. So each system has each trench has a subduction rate that was half the isolated single slab rate. And finally, if the trenches get very long, you get very, very slow rates of subduction. And I was going to talk just briefly an example about the Himalaya, where we can see double slabs, which have caused, I believe, the exceedingly rapid convergence of India and Eurasia. But we started late, and I know it's now 3:30, so 5 minutes? Okay, so I'll go through this fairly quickly. And this was done in collaboration with my colleague Oliver Yagutz at MIT. So you all know we start back here at 130 MA. Here's India. It's going to cross the entire Tethys and crash into Eurasia. And this is basically the rate at which it did so. Here's today. Here's 120 MA. And here's the rate going up to maximum rates here of about 150 millimeters per year. So after India rifted off of Eurasia, it underwent a relatively slow period of northward motion. Then its rates increased to about 150 millimeters per year. And then it dropped rather rapidly and at about 50 MA. This is usually considered to be the collision. And then kept moving after the collision at about 40 to 50 millimeters per year, which is usually suggested to be either ridge push or some kind of plume activity, more likely ridge push. And I'm going to basically demonstrate to you that we can explain basically every piece of this curve, including the ultra-high rapid rates of motion, as a story of subduction. So there are not one, but at least two subduction systems between India and Eurasia during its convergence. There's one that everybody knows about and talks about all the time, which is represented by this volcanic arc down here. This is the Andean arc. This is the Karakoram-Gandhisi belt. But there's also an intraoceanic arc, which was in the middle of the Tethys and is represented by the Kohistan-Ladakh arc here, which was also accommodating subduction of India. So right away from the results I've shown you, you may guess that this subduction system is going to want to go very much faster than a single subduction system. And importantly, these two subduction systems, with some complications over here in the western part, basically extended for 10,000 kilometers from Indonesia through the Himalayan region and all the way over into central Turkey. So 10,000 kilometer long, roughly parallel subduction systems. So if we look at the proposed situation after India starts to move northward, but before about 90 MA, we had one, actually more, subduction systems under Eurasia, more over here in the west, but let's just simplify this and imagine one, and a second subduction system here to the south, an intraoceanic subduction system. Now at 80 MA, something somewhat coincidentally happened at roughly the same time in the east and west. This intraoceanic system landed on top of Africa, creating the Somal ophiolite and the Peri-Arabian ophiolites, the Cyprus ophiolite, and basically became inactive. This eastern part basically landed here in Indonesia, and the arc, the Woyla arc, and the Andean arc both shut off at this time. So we've gone from two subduction zones 10,000 kilometers long to a long northern subduction zone, but a southern one only 3,000 kilometers long. So here in cartoon form, if you're going to model two 10,000 kilometer long belts, here a 10,000 and a 3,000. So what this means is that this asthenospheric material between these two subduction systems has to work very hard to get out of this long corridor as these two trenches converge. Whereas here, even though the gap between the two subduction zones is the same, this material gets out much more easily because it doesn't have to travel very far. Now this occurs at exactly the same time where we go from slow 40 millimeter per year convergence to 150 millimeter per year convergence. So this is the time period where those two arcs are becoming inactive, and we're going from a 10,000 kilometer long zone to a 3,000 kilometer long zone. So just to very quickly take you through the modeling, before India rifted off of Antarctica, these two subduction zones were already going. So there has to be a spreading ridge somewhere, and we don't know where the Paleo Ridge was. We put it right here in the modeling. And we actually have trouble keeping the double subduction rates this slow. They're both the result of two very long subduction zones and some younger material here going down the trench. Now, up until 80 to 90 million years ago, that subduction remains really slow, right in this region in here. But beginning at from 90 to 80, with the shortening of the southern subduction zone, we see, so the black is our modeling, we see the rate increase to about 150 MA. And all of the dots here are India, Eurasia reconstructions. The red line is Indian Ocean opening data. And basically what's happening is that we're going from basically we're just shortening this trench here, so we're changing the ratio between trench length and slab separation. So our analytical modeling gives us this peak at about 180. And you'll notice our analytical modeling, whether this is in fact reality or not, I don't know, but shows that after a maximum rate of 150, rates start to slow off even before collision. And this is actually probably the result of the fact that these two trenches are now getting closer and closer together. So basically, I'm going to skip a lot of stuff that you can see, and basically, which is all the geology, because I know that we are behind schedule. But basically, to say that we've done a number of paleomag studies to look at whether the Kohistan-Ladakh arc was in fact where we think it should be, down here at 80 MA. Or the conventional story where the Kohistan-Ladakh arc has already collided with Eurasia at 80 MA. And so we actually went in, added to the existing paleomag literature. In fact, Sonia Tiku-Schwartz is here. She did helped with some of the analysis on here. And we had a very well-dated section. And so between 66 and 62 MA, we put the volcanics of the Kohistan-Ladakh arc here down near the equator. So the story seems to hang together pretty well. So this is basically entirely a story of subduction. Slow subduction with two long trenches. One trench becomes very short. We get rapid subduction and convergence so that we have almost twice the convergence rate as we would expect across a single subduction zone. This is actually the collision with the Kohistan-Ladakh arc. The collision of India with Eurasia, which we now date as younger at about 40, and I don't have time to talk about any of that, occurs here and has very little signal. The convergence continues through here. And this has been ascribed to ridge push, which, as I said, I think it does very little to the system. And I'm going to tell you that even the post-collisional convergence is a story of subduction. Oops, I give these away. Here, the India-Eurasia collision zone is occurring along the northern boundary of what I'll call a combined India-Australia plate. It's not really a plate because it has a zone of extremely high compressional stress and buckling of the ocean floor in here. And everywhere along this part of this plate, we have subduction of old seafloor at about 60 millimeters per year. So what I'm going to propose is, in fact, the continued convergence of the Himalaya and Tibet is caused by ongoing subduction of old oceanic lithosphere here beneath Indonesia, north of Australia. That's exerting an enormous slab pull on this plate and pulling it to the north. And despite whatever resisting and compressive stresses we have in the Himalaya and Tibet, these enormous slab pull forces are enough to continue to move this plate to the north and are generating this intraplate buckling and shortening that we see in here. This has nothing to do with ridge push at all, which is not capable of generating these kinds of stresses. So as a result here, you can see that as this India-Australia plate continues to move to the north, we're not only going to be devouring this Eastern Pacific margin, but in fact, we're basically destroying much of Central Asia as we push India ahead of us. So how that's going to work in the future, I don't know. But in the interest of brevity, I have some conclusions. You can read them if you can read them. Otherwise, I just want to say that I've tried to give you an example of how some very simple principles can be used to understand the behavior of subduction systems, and that whether you have one slab or you have multiple slab systems, the same rules apply. So the regional circulation may be different for these more complicated systems, but the individual slabs respond to the pressures that they see in exactly the same way. So I thank you very much for your attention.